There is no also gradient flow, right? So usually in Morse theory, you use gradient flows to produce deformations between sub-level sets. So here the natural thing would be to use, one could try to use mean curvature flow, but actually mean curvature flow is very inefficient for these purposes. It quickly runs into singularities, and it's not well defined in this generality. So we have no gradient vector fields to use. And also, maybe this is a more technical thing, when the theory doesn't say that every limit guy will be smooth, right? It just says that there is a sequence that converges to a smooth guy. But maybe there are other mean-max sequences as well that converge to a singular configuration. So there's a possibility of non-smooth limits also poses serious difficulties.
Because when you say infinitely many, you mean infinitely many sigmas, I guess.
Sigmas, yeah, smooth.
And you get a sequence of sigmas where the area goes to infinity, or the area could go to something bounded but has higher and higher multiplicity.
The second possibility is potentially, this is a possibility, but we sort of believe, we believe that the areas must grow to infinity with multiplicity 1. So I'll mention some more precise conjectures about that. Yeah, but the way the proof goes is by contradiction, and in theory it could happen what you said. Yeah, so you see that these difficulties are there. And as I said, no information was given about the Morse index of these minimal surfaces. So these are smooth minimal surfaces. They have a finite Morse index. Of course, you expect that the Morse index must be related to the number of parameters. So that's the first theorem we prove. This is joint work with Andre. We prove that this heuristic that the Morse index should be related to the number of parameters that comes from finite dimensional Morse theory works here for the support of the minimal surface. So in other words, the index of the support. So the support would be the union of the sigma i's. It's bounded above by the number of parameters. K here is the dimension of the parameter space. Okay? So that's the first Morse index bound in the theory. Let me make one comment here. So when we were working on the Wilmer conjecture, on the Friedmann-Hay-Wang conjecture, the philosophy was that something like this should be true, but we didn't have that available at the time, so we needed to proceed indirectly. So now with this bound, one can proceed directly and have more direct proofs. Also, of course, this bound holds true for the families that we're producing using this RPK. So the index bound, the philosophy is that should give you a bound on the complexity of the hypersurface that you are producing. And we even conjecture that in some scenarios, for instance, in the positive curvature scenario, one should have that the sum of the Betti numbers of the surface must be bounded by a constant times the index. Okay, so in this theory, it's very hard to control the topology of the hypersurface unless you go through the index. Okay, so that's one content about the theorem. Right? So we also have the problem of multiplicity. So we have a conjecture for that. It's called the multiplicity 1 conjecture. What it says is the following. It says that for generic metrics, if you look at a two-sided unstable, stable means that its second variation is non-negative, right? So say it's an unstable component of a min-max minimal hypersurface produced by this theory should have multiplicity 1. Should have multiplicity 1. If things are one-sided, then it's a bit trickier because you can think of the double cover approaching that, and you have multiplicity 2. Well, let's say you have a two-sided component, then what we say is that at least if the metric is generic, this this phenomenon here should not happen. The multiplicity should be.
Positive curvature not being used.
No, yeah. Yeah, so these are the first estimates without the curvature assumptions, right? Yes. So this holds for general metrics. They don't have to be generic. We conjecture that for generic metrics, multiplicity should not happen. That's the multiplicity one conjecture. And what we proved, that's the first multiplicity one theorem in the subject, is that this conjecture is true for the setting of one parameter sweepouts. That's the traditional setting that goes back to Birkhoff. So theorem 2, again with Neves, is that this multiplicity one conjecture holds in the setting of one parameter sweepouts. So that's evidence for the conjecture. So as I said, this is the first multiplicity one theorem in the subject. And actually, let me make it a little bit more precise. Let's suppose that there are no one-sided hypersurfaces. Suppose there are no one-sided hypersurfaces. This is true if the manifold is simply connected or if it has no homology, Z2 homology in dimension n. Then we can give a more precise description of what happens. This is a complete characterization of the problem of index and multiplicity for the setting of one parameter sweepouts. Basically, we
Explain what these one parameter sweepouts are.
yeah. So the one parameter. What I mean by that, right? So for one parameter, what you can do is you can choose your favorite Morse function, f, right? So f is a Morse function. So you can consider the level sets of a Morse function. That gives an example of a sweep out, which is continuous in the flat topology and also in the F metric. Then you can take its homotop class. So by this result, pi 1 of that guy is isomorphic to Z2, so there is a generator. The generator is exactly that. So that's the class that I'm talking about. So when I say it goes back to Birkhoff, it was because Birkhoff introduced these types of sweepouts for surfaces to study the problem of closed geodesics. Yeah, so that's the most classic setting for Mimax. So for that setting, we proved that the minimum variety that you get has to be of the following form, has to be an unstable component. This is for generic metrics. Okay? Generic metrics. So the variety has to be an unstable guy with multiplicity 1, and that guy is unique, so it's a connected guy, plus perhaps a bunch of stable ones with multiplicities. So they have index 0.
Generic means bare category.
Yeah, you're right. Bare category, yes. Right. So these guys here have index equal to 0, and this guy must have index equal to 1. Okay, so the total index is 1. There's one component of index 1, and that component must have multiplicity 1.
So philosophically, if this would have multiplicity 2, it would behave like something with higher Morse index?
That's right.
It's sort of
Yeah,
moving way around.
right.
Why do you assume generic metrics on your conjecture? Do you have a counterexample for non-generic metrics?
So we don't have an example. We don't have any example where we have examples where multiplicity has to happen, but if you search somewhere else, it doesn't happen. So what I mean is it's related to this question, right? When you have the sequence of sweepouts, you're trying to take a limit, but there are several possible limits that you can take, right? So if you think of an example like this, take a very long cylinder and then identify these two surfaces here, then the optimal sweep out for this guy is like say this is sigma 0. The optimal sweep out is sigma 0 plus sigma of t. As t goes to 0, they cancel out, right? So as a chain, it actually goes to 0. And then you sweep out your manifold, ends as 0 as well, because these guys are identified. And the area is 2 times the area of a leaf. So the point is that this is optimal sweep out because the min-max number is exactly the sum of these 2 areas. And there's multiplicity here, because if I take TIs convert into 0, these guys, although they converge to 0 as chains, they converge to twice the fiber as varifolds. But in this example, there are lots of guys, there are lots of other critical points which you don't see multiplicity, right? So in other words, in this example, you can see that there must be multiplicity. But maybe if you search somewhere else, right, you find a multiplicity 1 guy. So that's the best we can do here. So certainly we expect that for generic metrics you can have multiplicity. Oh, sorry, for non-generic metrics, that's this case, you can have multiplicity. But perhaps things could be so good that maybe if you search somewhere else, you don't see it. So that's I guess the answer to your question. Right. So I guess I should. Are there any other questions? Yes.
How do you actually define index?
Okay, that's a good question. It's related to the first theorem I'll prove here. So for minimal surfaces, these minimal surfaces are smooth, then you have the usual notion of what index should be. But if somehow if your thing is singular, right, you don't have a good notion of index. So the way we do it for the first theorem is that we consider, let me maybe move into the proof, and that it's gonna sort of answer this question. I mean, any notion of index would have to have this property that, I mean, the index should be like the lowest k for which you can construct your guy with k parameter sweep outs, right? If you have a singular guy. So to prove these results, we actually prove 3 deformation theorems. So basically, you have to avoid the bad guys. You have a sequence of sweep outs. Maybe something wrong goes on. You have to be able to deform it and make sure that the bad guy doesn't happen. So first we have, you guys have 25 minutes. I'll sketch these results, okay? So there's a deformation theorem A. This guy is to avoid a sigma with index of the supportive sigma greater than or equal to k plus 1. Okay? So here the idea is the following. So suppose you have a sigma with index greater than or equal to k plus 1. This index here is in the traditional sense of minimal surfaces. Okay? So we have a k plus 1 dimensional family of surfaces nearby such that sigma is the maximum for the area. So in other words, if I draw the space of surfaces here, there's going to be a k plus 1 dimensional parabola here passing through sigma. And this k plus 1 dimensional parabola is obtained by applying diffeomorphisms to your sigma. So you can find a family of diffeomorphisms parameterized by a vector v in the ball, such that f0 is the identity. And then the area, when I look at the area function, sigma is the unique non-degenerate maximum point.
So you do it using the diffeomorphism
Yeah.
in the image. Yeah. Okay.
Right. So yes. So as a minimal surface, you have these normal variations, and then you extend them to be ambient vector fields. So I'm talking about ambient deformations of the space here. But very, very close to the identity. So this is a small deformation of sigma. Okay? And the area does like this. So the area function, let's see, v sends to the area of f v of sigma has this is a concave function and has a unique maximum point at the origin. And then what you realize is that this picture is actually is stable with respect to a varifold perturbation. So if you have an S nearby, just a varifold, you can apply ambient deformations to a varifold, and you use the same family for a varifold nearby, you're going to have a similar picture. So you're going to have, again, a parabola. Maybe your varifold is not the maximum point, right? But this picture that it must be concave and it must have a unique maximum point is preserved, as long as your deformation is not very, very big. So here taking, say, an S in a ball of radius epsilon naught centered around sigma in the F metric. So that's what you can do for varifolds nearby. And then the idea, as I said, this is, what do I mean by a deformation? Well, first you have your parameter space, X. Then suppose that you have a sequence of sweepouts, phi I. So this sequence is approaching my min-max number. So that means that the supremum of the masses is converging to the min-max number, right? And suppose that there is some sequence here which is converging to my bad guy. So I will have an island here where, say, I'm epsilon close to sigma. Maybe an even smaller island here where I'm epsilon over 2 close to sigma. And then you want to deform sigma away. Okay? So the idea now is that when I look at the corresponding varifolds, these guys are very close to sigma, where you have this k+1 dimensional parabola. So they have their own parabolas as well, because you can use the same family of diffeomorphisms. So the point is that if I pick an X here, and I look at the corresponding parabola, so maybe phi I of X is here, maybe the maximum point is some other guy. Maybe say the maximum point is achieved as some m of x, mi of x. So there's always a unique maximum point, and if this guy is not the maximum point, right, in my parabola, then I have a direction to push things down. Okay, that's the idea. I'm using its own parabola, right, to have the direction that points it down. So when I look at the union of this parabola, so basically I take the image under phi I of, say, this disk, say this region is D. This guy is k-dimensional, right? When I look at the corresponding maximum points, right, gives me some kind of k-dimensional submanifold as well, right? This mi k-dimensional as well. And they're all contained in this union over V in Vk+1 of the Fv phi I of x, where x is in D. And this region Q, again, this is just a sketch, is a 2k+1 dimensional region. So there's this transversality argument which tells you that, well, you have these two k-dimensional guys inside a 2k+1 thing, so you can perturb a bit, so you perturb phi I slightly to get some phi I prime that doesn't intersect the set of maximum points. And then once I'm sure that I'm not at the maximum point, I have a direction to push down. And you push down things. So there's a direction. So then you can push the area of Ti prime down. It's sort of like saying that, when the index is high, you have enough space to perturb things and so that you can avoid the critical point by pushing the area down. That's the principle that's displayed behind this technical situation. So we avoid that guy, right? But you have to do it countably many times, right? Because how are you going to be sure that you're avoiding all bad guys? So here's, I guess, this is related to Peter's question. Generic here means bumpy. There's a concept of Brian White which says that generic metric in the bare sense is bumpy. And bumpy means that the nullity is equal to 0 for every minimal hypersurface. So this fact, together with the compactness theorem that was proven recently by Sharp, says that if you're generic, then the set of minimal hypersurfaces is going to be countable. Okay, the set of minimal hypersurfaces is going to be countable. So for a generic metric, I can just deform the bad guys one by one, right? And making sure that when I deform one guy, I do not get a previous guy back. So the deformations have to be smaller and smaller. And then there's a diagonal argument here, which makes sure that bad guys won't appear in the limit. So that gives the result for bumpy metrics. And then you take a limit. There's this compactness theorem, which gives you the result, theorem 1 for general metrics as well. Okay. You have to be also a bit careful, because when you're pushing the area down here, you're still outside the bigger disk, right? So you have to make sure that the deformation of this guy does not get close to sigma again, and that we also separately do. Okay, so what's deformation theorem B? 15 minutes, and I have a theorem C also. So deformation theorem B is to avoid, say, something like m times sigma plus a bunch of other stuff, where m is greater than or equal to 2 and the index of sigma is equal to 1. So you want to avoid, again, so here, sorry, I'm already in the setting of one parameter sweepouts. So I want to rule out multiplicity, right? This guy, index 1 guy with multiplicity 2. So what's the idea? So you have your guy sigma. So as a minimal surface, it has index 1. So that gives you a one-dimensional parabola, right? Which makes the area down. So this is a one-dimensional. So the diffeomorphisms are just defined for a vector v minus 1, 1. Here is f minus 1 of sigma. Here is f1 of sigma. Just pushing the area down by using the fact that the index is equal to 1. So in principle, this is sort of problematic, because the philosophy again is that this should behave as higher index, right? But we don't have a two-dimensional family, because as the index just gives me a one-parameter guy. The other must come from the multiplicity. So the idea is to do the following. Suppose again, so this is your parameter space, X. Again, you're going to have this island where you're very close to this variety. Say this, you're epsilon close, and so that the endpoints say they're a distance precisely epsilon from being equal to this guy. So for each varifold here, you're very close to this guy, so there will be a parabola. So you can apply the parabola. This is just a pictorial illustration of the proof, right? So you can apply the parabola to each varifold here. Apply these deformations. And then in each such guy, there will be a unique maximum point, right? But then, in the worst case scenario, what could happen is that there is a maximum point here, then there's a maximum point there, and then crosses like this. Okay. So why is this the worst case scenario? Well, this tells me that if I want to deform the area of this guy down, I cannot go to the left, right? I have to go here. And again, when I'm at this other extreme here, if I want to deform the area of this guy down, I have to go in the other direction. So here I'm close to being f minus 1 of sigma. And on the other side, I'm close to being f1 of sigma. Okay? So the point is that I don't have much time to enter into technical details here, but one thing that you have to do is that when you do this deformation, you're going to be very close to this guy, right? Very close to this guy, but not exactly equal to. So we need to deform this guy further and connect precisely to that guy. So that's called interpolation. Okay, again here. And you have to do this interpolation so that the area doesn't go up by much. And there is a result like that. Basically, maybe if you allow me one statement here, you have this lemma that says that if you give me an L and you give me a delta, if you give me two chains with mass bounded by L, then I can find an eta such that if there are eta close in the flat distance, then one can interpolate between T1 and T2 with area at most L plus delta. Okay? So if you have two guys which are very close to each other in the flat topology, you can go from one to the other without perturbing the area much, just by delta. Okay? But the problem is that, when you're approaching the min-max number, your areas are just off by the limit by something that you cannot control. So you cannot really interpolate things at the maximum level. But once you made the area go down, you're already at a safe region where you can interpolate things and make sure that the area doesn't go above what you had originally. Okay? So these interpolation things are fine once I get the area to be really down by some amount. So you can connect these things by interpolation, and then the final idea is that you can really go from m times, so say the picture's like this. This is sigma. This is f minus 1 of sigma. And this is f1 of sigma. So once you made them exactly equal to m times f minus 1 of sigma and m times f1 of sigma, you can go from this configuration to the other one just by pushing one component at a time. Okay, so you can go, you can keep like m minus 1, f minus 1 sigma, plus this guy. So you sort of push one component at a time, and then you see that you can deform. You can go from m f minus 1 of sigma to m f1 of sigma with areas strictly less than m times the area of sigma. Just going one component over.
If you push them down far enough, they would be getting farther apart. They are in your picture. So, I mean...
These deformations look big, but they're actually small, right?
Well, I mean, I don't see how you can control the two numbers somehow.
Okay, so so one thing that you want to make sure that you don't destroy is that you are actually a sweep out. Okay, But that's fine. There's a uniform constant delta that if you're allowed to perturb things just by delta, you're gonna be a sweep out again. Okay, so these deformations are small in the sense that they won't destroy the property of being a sweep out. So, but do you understand the picture? So I'm sort of here I have to deform down, here I have to deform up, but later I can connect these two things. And I can connect them by this deformation where you pass one component at a time, and the areas are never equal to m times the area of sigma. Okay?
I just don't see how you can control both the area, I mean the distance from each other and how much down further the areas are down. Well, anyway.
Okay, maybe we can talk later. I have 7 minutes. Let me mention deformation theorem C. Right. So in deformation theorem C, what do you have to avoid? So we already know that I'm in the one parameter setting here. One parameter set for one parameter. I already know that the total index is bounded by 1. That was the first deformation. So there must be at most one component which is unstable, because the total index is bounded by 1. And I know that if such a component exists, it cannot come with multiplicity. But I also had the statement, I guess I haven't erased it yet, that such component exists. This was not even known, right? The guy is unstable. There must be an unstable component, was not even known. And that's the content of deformation theorem C, that you can avoid the variety to be a combination of stable guys. All index 0. Here I'm dealing with generic metrics, okay? So they cannot be stable. You must have an unstable component. So here the argument goes like, the stable component looks like a neck. Okay? And then once you have a neck, there's an area decreasing retraction. So say this is sigma I. The region says omega I. There's an area decreasing retraction. R I from omega I to sigma I. Okay, so the deformation looks like the following. Okay, so we'll erase this. So you might have more than one component. Your surface, is very close to a combination of these necks, but there might be some something with very small area connecting them, like in this picture here. And here you have some tubular neighborhood. And outside the tubular neighborhood, because they have to converge to the linear combination in varifolds, this happens to have very small area less than epsilon. So the first thing you do, this is actually based on a deformation used by my former student, Montezuma. You prove that you can deform this guy to something that is completely contained in a tubular neighborhood. So you can do surgery. You can kill your neck. Sorry. Okay, so you can get rid of this neck with area epsilon plus delta, where delta is arbitrarily small. That's the point. Arbitrarily small. The lower the delta, I can find the deformation that goes from this guy to outside the tubular neighborhood without adding delta of area. So once your thing is completely contained in a tubular neighborhood, you apply the retraction. So here's how the deformation looks like. Okay. So again, again, you have the picture where you have the island that you want to destroy. So the first thing you do is you do this surgery procedure, and then you can do this with area 1 over I. So you're not destroying the min-max property. And then here you're outside the tubular neighborhood. Sorry, inside the tubular neighborhood. And then you can apply the retraction. Retraction here. And the path is something that does this. So you just go around like doing this, okay? And you have to, I mean, I'm almost out of time, so you can argue that when you do this, you're sort of destroying the configuration that you had, and you're not adding anything back, okay? So that's the last deformation theorem I was just able to sketch. Maybe let me end with a conjecture. So the real point is, of course, we are interested in this infinitely many conjecture that we were able to solve in the positive curvature case.
You didn't say we use positive curvature.
Right, so okay. Yeah, so positive curvature enters into the picture because there's this property that when you have positive curvature, any two minimal surfaces must intersect. So the Gromov-Guth bound holds for arbitrary manifolds. That's okay. This sublinear growth. But the fact that it's like closed geodesics in positive curvature, the same property. They always have to intersect. So this theory always gives you an embedded guy. So this means that varieties like this cannot appear in min-max theory. So your variety has to be a single multiple of a single component. And that, you can argue that it runs into a contradiction with the sublinear growth in the areas. Yes. So in general, what we think is true, I mean, that's the picture that we have here, is that for a generic metric,
So this curvature condition.
no curvature condition here, yeah. Just generic. For a generic metric, there should be a minimal hypersurface sigma k of index equal to k. For each index, there should be a minimal surface. And the area of this guy grows like k to this power. So those are the surfaces that we believe they must exist because their existence is forced by topological principles, the fact that the space of cycles is RP infinity and that you can sort of run these ideas and get a bound of the Morse index. So in some sense what we're doing is in the conjecture and say that, well, probably what the road from here would be is to sort of like first prove a lower bound on the index, and then you can hope so that things can be traced back to the multiplicity 1 conjecture. Right? And then if you can prove the multiplicity 1 conjecture, you get a proof of that one too. So yeah, so that's sort of what we're doing right now. And thanks for the attention.